Welcome back. In this lecture I shall discuss refrigerants. So the specific objectives of this particular lecture are to discuss primary and secondary refrigerants, refrigerant selection criteria based on their properties, discuss classification of primary refrigerants, designation of refrigerants with examples, comparison of various synthetic and natural refrigerants, and finally some important features of refrigerant mixers. At the end of the lecture you should be able to differentiate between primary and secondary refrigerants, list important properties of refrigerants, classify primary refrigerants, write the chemical formula of refrigerant from their number, compare various synthetic and natural refrigerants, and list salient features of refrigerant mixers. So let me give a brief introduction. We know that the thermodynamic efficiency of a refrigerant system depends mainly on the operating temperature, that means the heat source and sink temperatures. However, important practical issues such as the system design, size, initial and operating costs, safety, reliability and serviceability, etc. depend very much on the type of refrigerant selected for a given application. Hence, selection of a suitable refrigerant is a very important step in the design of any refrigeration system. Okay. Refrigerants can be broadly divided into primary and secondary refrigerants. The primary refrigerants are used directly as working fluids in refrigeration systems. They undergo phase change while providing refrigeration, that means while flowing through the evaporator vaporization takes place, and while flowing through the condenser these refrigerants condense. Okay, so that they involve phase change processes, whereas secondary refrigerants are those liquids that are used to transport energy from one location to another. Unlike primary refrigerants, these secondary refrigerants do not undergo any phase change, and water and brines are the commonly used secondary refrigerants. If the operating temperatures are above 0 degree centigrade, then we can use pure water as secondary refrigerant. For example, pure water is widely used in large chilled water systems for air conditioning applications, etc. However, if the operating temperature is below 0 degree centigrade, that means for sub-zero temperatures we cannot use water because water freezes at 0 degree centigrade. So we have to use other secondary refrigerants, namely antifreezes or brines, and these kind of applications you encounter in cold storages or other frozen food processing applications, etc. The commonly used secondary refrigerants are the solutions of water and ethylene glycol, or the solution of water and propylene glycol, or the solution of water and salts such as calcium chloride, etc. In this lecture I shall not discuss secondary refrigerants, so the attention is primarily focused on primary refrigerants for Vapour compression refrigeration systems only. Let us look at refrigerant selection criteria. Selection of refrigerant for a particular application is based on the following requirements. The first requirement is thermodynamic and thermophysical properties. Second requirement is environmental and safety properties, and finally the third requirement is economics. So first let us look at the first requirement, that is thermodynamic and thermophysical properties. The requirements are like this. First, the suction pressure. At a given evaporator temperature, the saturation pressure should be above atmospheric for prevention of air or moisture ingress into the system and ease of leak detection. This is an important requirement, and also a higher suction pressure is better as it leads to smaller compressor displacement. Okay, that means at a given evaporator temperature the refrigerant selected should have a positive pressure, that means the operating pressure or the evaporator pressure should be above atmospheric. This is required because if there is any leakage will take place from the system to the surrounding, that means refrigerant leaks out from the system. Okay, this is easier to handle than the reverse case, that means if the system is operating under vacuum, then air or moisture from outside leaks into the system. Okay, this is difficult to handle because in order to remove the air or moisture, you have to do a complete overhauling of the system. Also, if the system is operating under vacuum, then detection of leak is difficult. Okay, so as far as possible, the refrigerant should have a positive pressure at evaporator temperature. Okay, also we know that when the suction pressure is high at a given temperature, then the density will be high or the specific volume will be low. Okay, that means for a given mass flow rate, the required size of the compressor will be small. Okay, for these reasons, the suction pressure should always be as high as possible. Okay, so this is the first requirement. The second requirement, discharge pressure. At a given condenser temperature, the discharge pressure should be as small as possible to allow lightweight construction of compressor, condenser, etc. So, unlike suction pressure, at a given condenser temperature, discharge pressure should obviously be as low as possible. Okay, this is because once it is low, we get the maximum operating pressure of the system will be low, because that is decided by the condenser pressure. Okay, once the maximum operating pressure is low, means the tubes chosen for condensers and the material chosen for compressor, etc., need not be heavyweight, right. That means you can go for thinner tubes, etc. Okay, so this reduces the cost and it also reduces the weight of the system. Okay, so this is an important requirement. Also, the pressure ratio will also be small when the condenser pressure is small. Okay, so that is the third requirement. That means the pressure ratio, which is nothing but the ratio of the condenser pressure to the evaporator pressure, should be as small as possible for high volumetric efficiency and low power consumption. And the fourth requirement is that the latent heat of vaporization should be as large as possible, so that the required mass flow rate per unit cooling capacity will be small. However, we find that the above requirements are somewhat contradictory, because the operating pressures, temperatures and latent heat of vaporization are related by Clausius-Clapeyron equation, and you know that what is Clausius-Clapeyron equation, that is given by this expression, ln P sat is equal to minus HFG by RT plus SFG by R, where HFG is the latent heat of vaporization, SFG is the entropy of vaporization, R is the gas constant and T is the absolute temperature. Okay, so using this equation, we find that this term, that is the entropy of vaporization, does not really change much. Okay, so if you assume that it is constant, then you can show that the pressure ratio, that is the condenser pressure divided by the evaporator pressure, is equal to exponential HFG by R multiplied by 1 by TE minus 1 by TC. Okay, so if the evaporator and condenser temperatures are fixed, let us say that these temperatures are fixed by the application and by the available heat sink, then you see that the pressure ratio increases as the latent heat of vaporization increases. Okay, that means if you want to have a refrigerant with high latent heat of vaporization, the penalty you have to pay is in the form of high compression ratio or the high pressure ratio. Okay, and high pressure ratio, as you know, leads to lower volumetric efficiency and lower volumetric capacity. Okay, so on the other hand, if you want to have a very low pressure ratio, then the latent heat of vaporization will be low. That means the required mass flow rate for a given capacity of the refrigerant system will be high. Okay, that means you have to handle a large amount of mass flow rate. Okay, this is again a disadvantage. Okay, this shows that a certain trade-off is required between the pressure ratio and the latent heat of vaporization. In other words, a trade-off is required between the COP and the volumetric capacity. Okay. Next comes isentropic index of compression. The isentropic index of compression should be small, so that the compressor discharge temperature will be low. We know that the discharge temperature is linked to the isentropic index of compression by the formula. For example, T discharge is given by T suction into Pc by Pe into gamma minus 1 by gamma. This formula we have used while discussing compressors, etc. So, here gamma is the isentropic index of compression. So, you can see that for a given pressure, compressor, condenser and evaporator pressures and given suction temperature, discharge temperature increases as your index of compression increases. Okay. So, this is not good from the compressor life point of view. So, in order to have a low discharge temperature, the value of gamma should be as small as possible. So, the next requirement is that the liquid specific heat. Liquid specific heat should be small, so the degree of subcooling will be large, leading to smaller amount of flash gas at evaporator inlet. Okay, so, we need small liquid specific heat. Next, vapor specific heat. Vapor specific heat should be large, so that the degree of superheating will be small. We know that when the degree of superheating is large, the suction temperature will be high. Okay, once the suction temperature is high, the density of the refrigerant at the entry to the compressor will be low. That means you require a larger compressor for a given mass flow rate. Okay, so this is not really good from a practical consideration. Okay, so as far as the vapor specific heat is concerned, we should have a high value of specific heat, but the liquid specific heat should be low. Again, we will find that this is contradictory. Okay, it is not possible to have a very high vapor specific heat and a low liquid specific heat. Okay. Next, liquid and vapor thermal conductivity. Both liquid and vapor thermal conductivity should be as high as possible for higher heat transfer coefficients. Okay. Next requirement is liquid and vapor viscosity. The viscosity of both liquid and vapor should be as small as possible for smaller frictional pressure drops. So, we find that the thermodynamic properties are actually interrelated, and they are mainly dependent on the normal boiling point, critical temperature, and the molecular structure. The normal boiling point indicates the useful temperature levels, as it is directly related to the operating pressures. Okay, so this is a very important property. Next comes critical temperature. So, what is the effect of critical temperature? If the critical temperature is very high, it yields higher COP due to smaller compressor superheat and smaller flash gas losses. Okay, so this is the advantage of having high critical temperature. On the other hand, when the critical temperature is high, we find that the vapor pressure will be low. Once the vapor pressure is low, the volumetric capacity will be low. Okay, so this is the disadvantage of having high critical temperature. So, you find that high critical temperature gives rise to higher COP, at the same time it gives rise to lower volumetric capacity. Okay, again you have to do a trade off between the volumetric capacity and the COP. Okay, and choose the critical temperature accordingly. This implies a need for a trade off between high COP and high volumetric capacity. And it is observed that for most of the refrigerants, the ratio of normal boiling point to critical temperature is in the range of 0.6 to 0.7. That means, this ratio is almost constant for most of the fluids. Okay. This means that the normal boiling point is also a good indicator of the critical temperature of the refrigerant, and this ratio is in the temperatures are in Kelvin. Okay. Only then this ratio holds good. That means, you have to use absolute temperature scale. Okay. When you are using absolute temperature scale for the normal boiling point and critical temperature, you find that the ratio is about 0.6 to 0.7. Okay. Now, properties such as latent heat of vaporization and specific heat depend on the molecular weight and structure of the molecule, and Troughton's rule shows that the latent heat of vaporization will be high for refrigerants having lower molecular weight. Okay. We have discussed Troughton's rule when while discussing thermodynamics. Okay. So, according to Troughton's rule, if the molecular weight of the fluid is low, that means it gives rise to higher latent heat of vaporization. Okay. This is an advantage. This is the reason why inorganic refrigerants, inorganic fluids such as water and ammonia, which have low molecular weight, always give rise to high latent heat of vaporization. On the other hand, synthetic refrigerants have high molecular weight, so their latent heat of vaporization is low. Okay. So, that is how the molecular weight and latent heat of vaporization are related. Now, the specific heat of refrigerant is related to the structure of the molecule, and a small value of vapor specific heat leads to dry compression, but higher degree of superheat. Okay. That means, when you have a small specific heat for vapor, then you find that when you are starting the compression, if the inlet to the compression process is on the saturated line, then you find that the exit is always in the superheated region. That means compression will always be a dry compression process. Okay, so this is a requirement if you are talking about reciprocating compressors and many other compressors. Okay, so from this point of view, a low value of specific heat is good. Okay, but if the specific heat is low, we find that the degree of superheat will be high. Okay, this is not desirable. Okay, so again you have to do some kind of a trade off, and again you find that there is an optimum value of vapor specific heat where the performance will be best. And it is also shown that the specific heat of vapor is related to the specific heat of the liquid. Okay, normally it is not possible to have as I have already mentioned, a high value of specific heat for the vapor and a low value of specific heat for the liquid, or vice versa. Okay, and it is observed that the optimum molar vapor specific heat is found to be in the range of 40 to 100 kilojoule per kilomole Kelvin. Okay. Next comes environmental and safety properties. Before I go to environmental and safety properties, there are also other thermodynamic properties which need to be considered. For example, one of the important properties, especially when we are dealing with very low temperature refrigeration, is the freezing point. Okay, the freezing point of the fluid should be lower than the lowest temperature that you encounter while operating the refrigerant system. Okay, this is required, otherwise the refrigerant may freeze while flowing through the system. Okay, so the freezing point should be as low as possible, right. Now let us look at the environmental and safety properties. This is a major factor in deciding the usefulness of a particular refrigerant. Normally the efficiency of the system mainly depends upon the thermodynamic and thermophysical properties of the refrigerant, and we have discussed the requirements, right. But it is observed that the finally whether the refrigerant can be used or not is decided not only by the thermodynamic and thermophysical properties, but mainly by the environmental and safety issues. This is the reason why refrigerants such as carbon dioxide or ammonia or sulfur dioxide, which give reasonably good performance, were phased out or thought to be not good because they have certain safety related problems. Okay. So, especially the refrigerants used in the olden days, they were good as far as the performance is concerned, but most of them used to have or used to create some safety related problems. Okay, such as toxicity, etc. That is the reason why they were phased out, and that is the reason why synthetic refrigerants were invented. Okay, so safety related properties are very, very important. Okay, now let us look at what are the environmental and safety related properties. These properties are the first property is ozone depletion potential. The ozone depletion potential, or the ODP, should be 0. Okay, and the ODP of a refrigerant or ODP of a fluid depends mainly on the number of chlorine or bromine atoms in the molecule. Okay, if the number of chlorine, and if the molecule contains chlorine or bromine atoms, then it will have a non-zero ODP value. Okay, and as per the Montreal Protocol, we have discussed this while discussing the history of refrigerants. As per according to the Montreal Protocol, we cannot use any refrigerant which has non-zero ODP value. Okay, that means all ozone depleting substances have been phased out or have to be phased out. Okay, so in future the refrigerants should be of non-ODS, that means non-ozone depleting substances. Okay. And the second important property is global warming potential, or GWP. GWP will be it should be as small as possible. That means refrigerant having high GWP are not recommended. In fact, the Kyoto Protocol, after the Montreal Protocol, several nations met at Kyoto Protocol, and under the Kyoto Protocol, several refrigerants which have high GWP values have come under the substances to be regulated. Okay, because high global warming potential means you have the greenhouse effect, and we have discussed this issue also earlier. So, the global warming is an environmental issue on global scale. So, it is not recommended to use refrigerants having high GWP values. Okay, even though there is no final decision as yet on the use of refrigerants having high GWP values, we really do not know, but in future they may be phased out. Okay. Next is what is known as the total equivalent warming index, or TEWI. Okay, TEWI. This is a new index, and this index takes into account the direct as well as the indirect contributions of a refrigerant to global warming. Okay, so global warming potential considers only the direct contribution of a refrigerant to global warming. What is the direct contribution of refrigerant? When the refrigerant leaks out into the atmosphere, that means when you release the refrigerant into the atmosphere, what is its contribution to global warming? Okay, this is considered while estimating the global warming potential. Okay, but the refrigerant can also contribute indirectly to the global warming. And what is this indirect contribution? This indirect contribution depends upon its energy consumption. Okay, if a refrigerant, or a system using a particular refrigerant consumes higher amount of energy compared to another refrigerant, then this particular refrigerant contributes to global warming indirectly, because higher energy consumption means higher burning of coal, etc. Okay, so this is the indirect contribution of a refrigerant. So these direct as well as indirect contributions of refrigerant have been taken into a single index, and this index is called as total warming TEWI. Okay, total equivalent warming index, and obviously the total equivalent warming index should be as small as possible for refrigerants. Okay. Next comes the toxicity. Obviously, refrigerant should preferably be non-toxic. Toxicity means this is related to the hazardous nature of the refrigerant as far as human beings are concerned. Okay, if a refrigerant is toxic, then if the person is exposed to such refrigerant, he will be suffocated. Okay, so obviously refrigerant should not be toxic, right? But we find that toxicity is a relative term. So what do we mean by toxicity is a relative term? Except air, all the fluids, theoretically all the fluids are toxic. That means when you are exposed to all the fluids other than air in sufficiently large concentrations, then people suffocate. Okay, so in that way all the fluids are toxic, but some of the fluids are more toxic than others. Okay, so how do we rate the toxicity? The toxicity mainly depends upon what is the degree of concentration at which human beings begin to get suffocated. Okay, so the concentration is important. Second factor is the time of exposure. Okay, how long a human being has to be exposed to a particular concentration of a particular fluid, so that he will begin to get suffocated. Okay, so these two aspects have to be considered, right? So toxicity, as I said, is a relative term which becomes meaningful only when the degree of concentration and time of exposure required to produce harmful effects are specified. Okay. Refrigerants such as R12 and R22 are non-toxic in the presence of air. However, in the presence of an open flame, they decompose and release harmful gases such as phosgene. Okay. This is again an important issue. So if you release R12 into atmosphere or R22 into atmosphere, and if there are no open flames or there are no heating elements, etc., then there is no problem, provided of course its concentration is not too high, right? But if there is an open flame, then the R12 decomposes in the presence of open flame and air, and it releases very dangerous gases such as phosgene. Okay, they are poisonous gases. Then if the human being is exposed to such condition, then he will get affected drastically. Okay, so ultimately the toxicity depends on many other issues, right? The concentration and the time of exposure and the conditions, right? And normally whether a particular refrigerant poses the problem of toxicity or not depends upon what is the amount of refrigerant that you are using in what space. Okay, so if you are using a small amount of refrigerant in a large space, so even when all the refrigerant is released into the space, then the concentration will be small, so it will not really give rise to any serious problem. On the other hand, if you are releasing large amount of refrigerant into a small volume or small space, then obviously the danger will be greater. Okay. So as I said, amount of total refrigerant used versus space is also important. Next comes the flammability. Obviously the refrigerant should be non-flammable preferably, and it should also be non-explosive. Okay, but we find that sometimes we cannot avoid using flammable refrigerants. Okay, so in such cases special precautions should be taken to avoid accidents. Okay, that means the design has got to be different if you are using a flammable refrigerant. Okay, so you have to make sure that there are no ignition sources. Okay, and you also have to take higher precautions to prevent leakage of the refrigerant. Okay, so basically the way how you handle flammable refrigerant will be different from the way you handle non-flammable refrigerant. Okay. And ASHRAE, that is American Society for Heating, Refrigeration and Air Conditioning Engineers, has divided the refrigerants into 6 safety groups, and these 6 safety groups are A1, A2, A3 and B1, B2, B3. Okay, these are the 6 groups, and refrigerants belong to group A1. Okay, for example, R11, R12, R22, R134A, R744, R718 are least hazardous, while refrigerants belonging to group B3, for example R1140, are most hazardous. Okay, so if you look at if you know to what group a particular refrigerant belongs, then you know whether it is really dangerous or hazardous or not. Okay, so this is the advantage of knowing to which group a particular refrigerant belongs. Okay. Other important properties are chemical stability. Okay, as far as possible, the refrigerant used should be chemically stable as long as it is within the system. Okay, so if it is once it is released into the atmosphere, even if it breaks down, that is not a problem. Okay, in fact, in the aftermath of your ozone layer depletion, it is observed that if it breaks down when it is released into the atmosphere, it is good, because the refrigerant will not go to the stratosphere or anything. But as long as the refrigerant is within the system, it should not break down. Okay, under any circumstances, that means even when it is exposed to higher temperatures, for example in the compressor. Okay, that means it should be chemically stable, right. Second requirement is the compatibility with common materials of construction. The common materials of construction are both metals as well as non-metals. This is a very important practical requirement. The refrigerant that you use should be compatible with almost all materials of construction, such as materials used for constructing the heat exchangers, various seals used in the system, various plastics used in the system, etc. Okay, it should not react with any of these materials. Okay, and next, miscibility with lubricating oils. Miscibility with lubricating oils is a very complex issue, because it is not necessary that the refrigerant should be completely miscible with a lubricating oil. Okay, if a refrigerant is not at all miscible with lubricating oil, for example ammonia is not at all miscible with lubricating oil, then all that we have to do is we have to install an oil separator at the exit of the compressor, so that you can collect the oil from the refrigerant vapor and send it back to the compressor. Okay, so that the oil does not circulate through the system, right. On the other hand, if you have a refrigerant such as R12, which is completely miscible in the refrigerant, then also there is no problem, because since it is miscible, oil is miscible with the refrigerant, oil will circulate along with the refrigerant, and if you take care of the design of the evaporator tubes, etc., then oil will come back to the compressor. Okay, so in principle there is no problem with refrigerants which are completely miscible and which are not completely miscible. Okay, but problem comes with refrigerants which are partly miscible. Okay, partly miscible refrigerants such as R22, you have to take extra care to make sure that the lubricating oil is coming back to the compressor. Okay, so you must know the relationship between the lubricating oil and the refrigerant. Okay, so this has a bearing on the design of the system. Then dielectric strength. Dielectric strength is very important in systems using hermetic compressors. We know that in hermetic compressors, the refrigerant comes in contact with the electrical winding of the motor. Okay, so the dielectric strength of the refrigerant should be high, so that it will not break down. Okay, this is not very important when you are talking about open type of compressors. Okay. Next important practical property is the ease of leak detection. Okay, if the refrigerant leaks out of the system, you should be able to detect it immediately using some means. Okay, if you are not able to detect the leak, then you do not know that refrigerant is leaking out of the system. Okay, what happens when refrigerant is leaking out of the system, and if you are not able to detect it, first effect is obviously the performance of the refrigerant system gets affected. Okay, and second problem is that it may lead to other problems like suffocation, etc. And third problem is that you cannot take, if you know that there is a leakage, immediately you can take some some measure, so that before it is too late you can correct the problem. On the other hand, if you cannot detect the leak, then all the refrigerant may leak out, and that may lead to major overhauling of the system. Okay. So the refrigerant used should be such that you must be able to detect its leak. Okay. There are various methods of detecting leak of a refrigerant. Okay. For example, if you are using ammonia, then you do not need anything, because your nose itself is the best leak detector, because ammonia has a very strong odor. So immediately you know that it has leaked out. Okay. On the other hand, some of the refrigerants such as R12, R134, etc., you have to use some special leak detectors, okay, like halide detectors or electronic leak detectors, etc., to detect the leak. Okay. So this is again an important practical requirement. Then what are the important economic properties? Important economic properties are obviously the refrigerant cost. It should be as cheap as possible, so that your initial cost will be low, and it should be easily available. Okay. So availability is also an important practical issue, right. So these are the important properties which decide the selection of a particular refrigerant for a given application. Okay. There are so many requirements, and an ideal refrigerant should meet all these refrigerants, all these requirements. Okay. But you find that in practice there is nothing like an ideal refrigerant. That means you do not have an ideal refrigerant at all. Okay. So you always have to balance between various requirements, and ultimately you do some kind of an optimization and select a suitable refrigerant. Okay. Now let us look at the classification of refrigerants. Refrigerants can be broadly classified into pure fluids and mixers. Okay. So under pure fluids, again you can have synthetic refrigerants. Okay. For example, chlorofluorocarbons CFCs, hydrochlorofluorocarbons HCFCs, or hydrofluorocarbons. These are synthetic pure fluids. Okay. You can also have natural refrigerants. Again, natural refrigerants can be organic, that means they are basically hydrocarbons, or inorganic. Inorganic means you have ammonia, carbon dioxide, water, sulfur dioxide, etc. Okay. So all these are pure fluids. Okay. Under mixers, you have azeotropic mixers and you have geotropic mixers. Okay. So this is how you can broadly classify refrigerants. Now let us look at designation of refrigerants. Since a large number of refrigerants have been developed over the years for a wide variety of applications, a numbering system has been adopted to designate various refrigerants. Okay. There are in fact hundreds of refrigerants which are used in a wide variety of applications. Okay. So it is very difficult to identify them or to designate them by their chemical composition or anything. Okay. So as a result, people have devised a numbering system. So if you look at the number, or if you know the number of the refrigerant, then you can get some very useful information regarding the refrigerant. Okay. So from the number one can get information about the type of refrigerant, its chemical composition, molecular weight, etc. All the refrigerants are designated by R followed by a unique number. So first let us look at fully saturated halogenated components. So these are derived from alkanes. Alkanes, as you know, have general formula CnH2n plus 2, and examples of alkanes are, for example, methane. Okay. As I said, these are fully saturated halogenated components. That means they are derivatives of either methane, okay, ethane, propane, etc. Okay. So what do we mean by halogenated? What is done here is the hydrogen atom is partly or fully replaced by other atoms, for example, atoms of chlorine, fluorine, bromine, etc. Okay. And always the formula will be something like this. That means if you look at the total number of the atoms in the molecule, you will find that it is equal to n plus 2n plus 2. Okay. So these are fully saturated halogenated compounds. Okay. These refrigerants are designated by R, X, Y, Z, okay, where X, Y, Z are numbers, okay, where X plus 1 indicates the number of carbon atoms, Y minus 1 indicates number of hydrogen atoms, and Z indicates number of fluorine atoms, and the balance indicates number of chlorine atoms. Okay. If there are only 2 digits, that means the value of X is 0. That means if you have R12, there are X in X, Y, Z, if you have only R12, okay, that means X is equal to 0. Okay. So, let me give an example. Let us say that the number is R22. There are only 2 numbers, that means X is equal to 0. Okay. X is 0 means the number of carbon atoms is 0 plus 1, that is equal to 1. Okay. Number of carbon atoms is 1 means this refrigerant is a derivative of methane. Okay. That means it will have a formula like CH4. Okay. Next, Y is equal to 2, that means number of hydrogen atoms is equal to 2 minus 1, that is 1. Okay. Next, Z is equal to 2. Okay. So, I hope you are getting this. We are saying R22 here X, this is nothing but R X Y Z. Okay. Since there are only 2 numbers, so this is R022. Okay. 0 is a number is nothing but X, so 0 is omitted and we are simply showing it as R22. So, X is equal to 0, Y is equal to 2 and Z is equal to 2. Okay. So, from the general formula you find that X is Y is 2 means number of hydrogen atoms is 2 minus 1, that is 1, and Z is 2 means number of fluorine atoms is equal to 2, and the balance, what is the balance? There should be 4 hydrogen atoms, that means the balance is 4 minus number of hydrogen atoms plus fluorine atoms. Okay. So, here number of hydrogen atoms is 1 and number of fluorine atoms is 2. So, the balance is 4 minus 1 minus 2, that is 1. Okay. So, number of chlorine atoms is 1. Okay. That means this particular refrigerant R22 will have 1 carbon atom, 1 hydrogen atom, 2 fluorine atoms and 1 chlorine atom. Okay. That means its chemical formula is CHClF2. Okay. So, it is very easy, once you know the basic rule, then just by looking at the number you can get its chemical composition. Okay. This is the advantage of devising this kind of a number system. Okay. So, using the same rule you can show that the formula of, for example, R12 is CCl2F2, that means it is a chlorofluorocarbon, and the chemical composition of R134A is C2H2F4. Okay. This is the derivative of ethane because you have two atoms of carbon. Okay. Here A stands for example, in R134A, okay, the letter A stands for an isomer. Okay. That means you can have a refrigerant R134 and a refrigerant R134A. Okay. So, both R134 and R134A have the same chemical composition, but different atomic arrangement. Okay. That means the arrangement of your atoms will be different. So, the molecular weight and chemical composition everything will be same, but atomic arrangement will be different, and such kind of molecules are called as isomers. Okay. You know that they are called as isomers, and because of the different molecular arrangement they give slightly different properties. Okay. Next comes your inorganic refrigerants. These are designated by number 7 followed by the molecular weight of the refrigerant. Okay. The molecular weight is rounded off. For example, ammonia has molecular weight of 17, so its number is R717. Okay. The 7 shows that it is a inorganic refrigerant. Okay. Similarly, carbon dioxide CO2, its molecular weight is 44, so its number is R744. Water molecular weight is 18, so its number is R718. Okay. So, that means the last 2 digits shows its molecular weight. Air has a molecular weight of 29, so its number is R729. Similarly, sulfur dioxide for example, its molecular weight is 64, so its number is R764. Okay. Next, the third category is mixers. All azeotropic mixers come under 500 series, that means R500, R501, R502, etc. Okay. So, letter 5 or 500 series means that it is a mixer and it is an azeotropic mixer. Okay. All geotropic mixers have been given 400 series this thing. Okay. That means R404, 407, 410, etc. Okay. Let me give an example, azeotropic mixers R500. This is a mixer of R12 and R152A. Okay. Of course, looking at the number 500, you cannot say it is a mixer of what, but all that you can say is that it is an azeotropic mixer because it starts with 5. Okay. You cannot say its composition or its weight percent or anything. Okay. Similarly, R502 is a mixer of R22 and R115. Okay. Here this is weight percent. For example, R502, R22 has 48.8% by weight, R115 is 51.2% by weight. Next comes geotropic mixers, for example R404A. Again the letter 4, that means the 400 series, means that it is a geotropic mixer. It is a mixer of R125, R143A and R134A. Okay. Here the letter A, that means the capital letter A, does not mean that it is an isomer. Okay. So, to distinguish between isomers and others, if you find that it is a small letter A or B, okay, small letters A, B, etc. indicate isomers. Okay. Whereas capital letter A means it is a mixer. Okay. Then again you can have R407A, it is a mixer of R32, R125 and R134A. So, last category is hydrocarbons. Saturated hydrocarbons, for example propane. Okay. Propane is as you know, it has a formula, chemical formula of C3H8. So, you can apply the same rule that we have applied for fully halogenated hydrocarbons, and you can show that its number is R290. Okay. Because here number of carbon atoms is 3. So, this 2 is you have this 2 here because X is 2, right. X is 2 means number of carbon atoms is 2 plus 1, that is 3. Okay. And Y is 9 here, that means number of hydrogen atoms is 9 minus 1, that is 8. Okay. Here Z is 0, that means it does not consist of any fluorine atoms. Okay. So, since it is balanced, you do not have any chlorine atoms also. Okay. So, propane follows the rule given earlier, but problem comes when you have to give a number for N-butane, for example. N-butane has a chemical formula of C4H10. Okay. So, you cannot give you cannot apply the earlier rule, because if you are applying the earlier rule, you find that a number of hydrogen atoms is 10. So, the Y value will be 11. Okay. So, Y value 11 means it has 2 digits. Okay. So, that leads to confusion. So, as a result, this N-butane has been given an arbitrary number, that is R600. Okay. Similarly, you have isobutane. Isobutane also is an isomer of butane, and its chemical composition is same as N-butane, that is it is C4H10, and it is given a number R600A. Okay. Again here the small letter A means that it is an isomer. Okay. You can also have unsaturated hydrocarbons, for example R1150. Okay. Here it is 4 digits, unlike the other refrigerants you have 4 digits here. 4 digits indicates that it is an unsaturated hydrocarbon. Okay. So, the first digit 1 means that it is an unsaturated hydrocarbon, and the other letters you can again apply the rule and you can get the chemical composition. For example, second letter 1 means that number of carbon atoms are 2, third letter Y means that number of hydrogen atoms are 4. Okay. Fourth letter 0 means that number of fluorine atoms are 0. Okay. Similarly, R1270. Okay. This is C3H6, that is it is propylene. Okay. So, that is how the numbering system is being used, and so this is the, you have to keep this in mind, so that you can, once you know the number, you can immediately. Nobody whenever you talk about refrigerant, normally we designate it in terms of numbers only. Okay. Because the chemical formula or the chemical names are very long. Okay. And always mentioning it in terms of the chemical names can be confusing. Okay. Next, let us look at the comparison between different refrigerants. Synthetic refrigerants. Okay. Synthetic refrigerants that were commonly used for refrigeration, cold storage and air conditioning applications are R11, it is a CFC 11 chlorofluorocarbon, R12, that means CFC 12, R22 HCFC, that is hydrochlorofluorocarbon 22, R502 is an azeotropic mixture of CFC 22, I am sorry. Okay, there is a mistake here. R502 is a mixture of HCFC 22 and CFC 115. Okay. Then these were used very widely but these refrigerants had to be phased out due to their ozone depleting potential. That means all these refrigerants have non-zero ODP values. Okay. So, due to this Montreal protocol, all these refrigerants were already phased out or they have to be phased out. Okay. The synthetic replacements for the older refrigerants are R134A. This is a HFC, that means it is a hydrofluorocarbon, it does not contain chlorine. Okay. So, its ODP value is 0, so it can be used, right. So, this is one of the synthetic replacements for the older refrigerants. In addition to that, the various blends of hydrofluorocarbons are also being used as synthetic replacements. Generally, synthetic refrigerants are non-toxic, non-flammable and are compatible with various materials of construction. So, these are the main advantages of synthetic refrigerants. However, compared to the natural refrigerants, these synthetic refrigerants offer lower performance and they also have higher global warming potential. Okay. Normally, you find that their COP values are much lower than the natural refrigerants. Okay. That means efficiencies are lower. Okay. Also, the thermophysical properties are also not as good as that of natural refrigerants. Okay. And in addition to this, they also possess high global warming potential. Okay. As a result, so all the synthetic refrigerants face an uncertain future. Okay. Even though right now there is no ban on them, we really do not know. Okay. In future they may be banned or they may be phased out. Okay. The oldest and most commonly used natural refrigerant is ammonia. Okay. If it is more than 100-year old and it is still being used very widely. Ammonia has excellent thermodynamic and thermophysical and environmental properties. It is inexpensive, it is easily available. However, it is toxic and it is not compatible with some of the common materials of construction such as copper or brass. Okay. So, these are the disadvantages of ammonia. Okay. Toxicity, incompatibility with common materials. It can also be flammable under certain conditions. Other natural refrigerants that are being suggested are hydrocarbons and carbon dioxide. Okay. Hydrocarbons and carbon dioxide were used in the olden days. Okay. If you remember our lecture on history of refrigerants, these were very widely used in the early days of refrigeration. Okay. But later they were phased out because of some perceived problems such as flammability and low critical temperature, etc. Okay. But they have made a strong comeback because of their excellent thermodynamic and thermophysical properties and mainly because of their environmental friendliness. Okay. So, as I said, in spite of some practical problems, these refrigerants are being considered as they are environmentally safe, inexpensive and offer good performance. Now, let me show some commonly used refrigerants and their salient features and properties. Okay. So, first refrigerant is R11. R11 is a chlorofluorocarbon. Okay. So, it is a CFC. Right. It has a normal boiling point of 23.7 degrees centigrade. Since its normal boiling point is quite high, that means it is 23.7 degrees centigrade, its operating pressures will be low. That means if you want to use it for air conditioning applications, say at 7 degrees evaporator temperature, that means the evaporator will be operating at under vacuum condition. That means the pressure will be subatmospheric. Okay. So, this is a disadvantage of R11. Okay. And the specific volume of the refrigerant will be very high because the pressures are low. Okay. So, these are two disadvantages of this particular refrigerant. However, since it has other advantages, this is still used and it is mainly used along with centrifugal compressors. Okay. It is used with centrifugal compressors because of its high specific volume. Okay. And its latent heat of vaporization at normal boiling point is 182.5 kilojoule per kg. Its critical temperature is almost 198 degrees centigrade, which is good, and its isentropic index of compression is 1.13. Okay. And its ODP is 1 and its GWP is 3500. Okay. Since its ODP is 1, this is banned. Okay. It is a ozone depleting substance, right. So, it is no longer used. And what were its applications? Its major applications were in large air conditioning systems, in industrial heat pumps because of its high critical temperature, and it was also used very widely as foam blowing agent in polyurethane foams, etc. Since it is phased out, substitutes suggested in its place are R123, and R123 can be used in older R11 systems or in new systems also. Okay, that means it can be retrofitted and it can also be used in new systems. Then R141B, R245FA and N-pentane. Okay, mainly R145B and N-pentane are used as foam blowing agents in place of R11. Okay, next you have R12, another very popular refrigerant. This is also a chlorofluorocarbon. It has a low normal boiling point of minus 29.8 degrees centigrade. That means its evaporator pressures will be higher than atmospheric if its evaporating temperatures are above almost minus 30 degrees centigrade. Its latent heat of vaporization is 165.8, critical temperature is also high, 112.04 degrees centigrade. Cp by Cv value is 1.126. Major problem is it is also having high ODP, that means ODP is 1, and GWP is also very high. So this is also banned. Okay, and before the ban it was widely used in domestic refrigerators, small air conditioners, water coolers and small cold storages. Since it has to be phased out, replacements have to be found for it. The most popular replacement for this is R134A in domestic refrigerators and small water coolers, air conditioners, etc., and blends of hydrocarbons. Okay. In addition to this, the other refrigerants replacements are also shown here, like R22, 227EA, etc. Okay. Next is R22. This is a hydrochlorofluorocarbon. This is another very widely used refrigerant, and it has a normal boiling point of minus 40.8 degrees centigrade. And it also has a reasonably high latent heat of vaporization of 233.2 kilojoule per kg, but it has a lower critical temperature of 96 degrees centigrade compared to R12, and its Cp by Cv value is also relatively higher. So that means its discharge temperatures will be high, and its ODP value is non-zero, but it is quite low. Okay, so it has a ODP value of 0.05. So it is also a substance which has to be phased out, but unlike R12 and R11, some time is allowed for this for phasing out. Okay, so you can use it till almost 2030. Okay, so you can still use it. It also has a global warming potential, and it is mainly used in air conditioning systems and cold storages. Okay, and since it also has got to be phased out, some substitute have to be found. Okay, again these are the major substitute. You can see that according to our numbering system, all these 410, 410A, 410B, 417, etc. are geotropic refrigerant mixers. Okay, whereas 507, 507A are azeotropic refrigerants. Okay, and you can also replace R22 by ammonia, that is R717, but not as a retrofit but as a new system. Okay. Another important refrigerant is R134A. This is a hydrofluorocarbon. Its properties are almost closest to R12. Okay. It has a normal boiling point of minus 26.15 degrees centigrade. Its latent heat of vaporization is good. Critical temperature, etc., are also shown here, and it is used mainly as a replacement for R12 in domestic refrigerators, water coolers, automobile air conditioning systems, etc. Okay. No replacement is required as yet because its ODP value is 0. Okay. There are some problems with this. The problems are it is immiscible with mineral oils, so you cannot use mineral oils as lubricants, so you have to go for synthetic lubricating oils, and it is also highly hygroscopic. Next comes refrigerant ammonia, R717, and its normal boiling point is almost minus 33 degrees centigrade. It has a very high latent heat of vaporization at normal boiling point because of its low molecular weight. Okay. Its critical temperature is also quite high. Its Cp by Cv value is high, which is a disadvantage. So you have to use water cooled compressors to keep the compressor temperature low. Okay. It is excellent as far as its environment friendliness is concerned because its ODP is 0, GWP is also 0. So its major applications are in cold storages, ice plants, in food processing, and in frozen food cabinets, etc. Okay. You do not require any replacements for this. Some problems are it is toxic and flammable, and it is incompatible with copper and brass. Advantages are it is highly efficient and it is inexpensive and widely available. Next comes R744, this is carbon dioxide. It has a very low normal boiling point of minus 78.4 degrees centigrade, but still its freezing point is about minus 56 degrees centigrade. So you cannot use it for temperatures below minus 56 degrees centigrade because of its freezing point. Okay. And it also has good latent heat of vaporization. major problem with this is its critical temperature is very low. Okay, that is the reason why it was phased out. But alternate cycles have been devised, that is transcritical cycle, where the condensation process is replaced by a gas cooling process, and this is made a strong comeback because of this reason. That means because of the modification in the cycle. Okay. Other important properties are it has a low ODP, and it also has it has non-zero ODP. Okay, I am sorry, and it has very low GWP. Okay. And its major applications are in cold storages, in air conditioning systems, in simultaneous cooling and heating. If you are using a transcritical cycle, you do not require any replacement. And major disadvantage is low critical temperature and high operating pressures. Okay, I did not mention this, but its operating pressures are very high, and it is eco-friendly, and it is inexpensive and easily available. Next is water, that is R718. Major problem with water is its high normal boiling point of 100 degree centigrade. Okay, that means your operating pressures will be under high vacuum. Okay, since it has a low molecular weight, its latent heat of vaporization is very high. It is an excellent from this angle. Its critical temperature is also very high. It is very good. The problem, of course, is Cp by Cv value is high. It is perfectly environmental friendly because its ODP is 0 and GWP is very low, and its major applications are as refrigerant in absorption systems and as refrigerants in steam jet systems. Okay, and its features are you do not require any replacement because of its excellent environmental properties. Disadvantage is high normal boiling point, okay, and high freezing point, so you cannot use it for sub-zero temperatures. Large specific volume, so you cannot use reciprocating compressors or anything because of this. Large specific volume is because you are operating the system at very low pressures. So its main advantages are eco-friendliness, inexpensive, and availability. Next is R600A. This is isobutane. This is a hydrocarbon. Okay, so its normal boiling point is minus 11.73 degrees centigrade. Its latent heat of vaporization is reasonably high. Its critical temperature is very high. Cp by Cv value is low. It is good. Its ODP is 0, so it is perfectly safe as far as ozone layer depletion is concerned. GWP is also very low. Okay, so this is used as a replacement for R12 in new systems. You have to change the compressor in domestic refrigerators, water coolers, etc. Okay, its features are you do not require any replacements. Its main problem or main concern is it is highly flammable, and its main advantage is it is eco-friendly. Okay. So this table is not actually comprehensive because there are many other refrigerants with many other features and many other problems also. Okay. Now let us briefly look at refrigerant mixers. Refrigerant mixers are mixers of 2 or more pure refrigerant fluids. The refrigerant mixers can be divided into, as I said, azeotropic mixers, geotropic mixers. The azeotropic mixers are usually binary mixers that behave like a pure fluid. Okay, so for all practical purposes, they behave like a pure fluid. Okay, the example is R502, which is a mixer of R22 and R115. This was mainly used in cold storages, etc. But this is banned because of R115, which is a ozone depleting substance. Then you also have R410A. Okay, this is R32 plus R125. Even though this I am calling it as an azeotropic mixer, its number is 4. This is what is known as a near azeotropic mixer. Okay, that means its temperature variation during phase change is very small. Okay, it is a replacement for R22. Geotropic mixers exhibit a significant temperature variation during constant pressure phase change process. That means when evaporation or condensation is taking place at a constant pressure, temperature does not remain constant. Okay, for pure fluids temperature remains constant, but that means the process is isothermal, whereas for geotropic mixers temperature of the refrigerant varies during phase change. Okay, so this is a major difference. Also at equilibrium the composition in vapor and liquid phases will be different. Okay, so these are the differences between geotropic and azeotropic mixers. Examples of some geotropic mixers are R404A, which is a mixer of R125, R143A and R134A. Okay, this is mainly used in place of R22. Then you also have R40. This is a mixer of 32, 125 and 134A. Okay, this is also used in place of R22. Then you also have R407C, which is used in place of R22. Okay. Then mixers offer the advantages of tailoring the composition to suit various temperature requirements. This is a major advantage of mixers. It is also possible to control the properties such as toxicity, flammability, oil miscibility by manipulating the composition. Hence, they are finding greater use. Okay. However, since the composition of geotropic mixers change due to leakage, this is a major problem. Use of these substances require greater care. Okay. And design of equipment such as evaporators and condensers is also complex because of the temperature variation during evaporation, condensation, etc. In the next lecture, I shall take up air conditioning. Okay. Thank you.